Okay, so this is part 2 of the Solomon's Chapter 11 practice problem solutions, and I got kicked off. My phone ran out of space, so you'll see that I've done some work here, but I'm just going to work this on a separate page. So, I was finishing up question 7 as I got cut off. So, the last step that we were talking about here is you're going to get an elimination before you can do the addition of the alcohol. You need this elimination, and the elimination needs to form the Synthesize. That's the more substituted product, or the Hoffman product. That's the less substituted product. So you need the Synthesize more substituted is going to go here. The Hoffman less substituted is going to go here. Well, if we want to add an alcohol on the end of the chain, we need the alkene on the end of the chain, which means we're going to need the Hoffman product. The way I remember this is Synthesize, I think that's how you spell it, is more substituted, and those both start with an S. And then the Hoffman is the opposite of that. So to get the Hoffman product, we need a big bulky base. So this potassium tertbutoxide is the big bulky base that we're looking for. Because if you have a narrow base, it's going to have a much easier time going in and getting the proton from the more substituted side. So that's a review of the reactions with the alkenes from Chapter 8. It's just a brief review, but that is a review really of reactions of alkenes completely from Chapter 8. Okay, and then we're going to do this question 8. So you can see my work. I didn't realize my phone had cut off, so I was still working at this. So I'm just going to work it through for you again. So the practice problem here is asking how you can accomplish this transformation. Basically, how can you go from an alkene to an alcohol? And so we have 3 main options of adding an alcohol, or water, if you want to think of it as adding H on one side and OH on the other, across a double bond. There's acid catalyzed, and acid catalyzed is going to have a carbocation that occurs first. So you'll add a proton, this will attack the H+, and you'll add a proton on one side and a carbocation on the other. And then that carbocation can undergo rearrangement, where this methyl group basically just shifts over to fill in those loss of electrons. And you have your carbocation trade places. Let's just say they like trade places. It's like a switcheroo here. Then after rearrangement, your water will attack OH2 or H2O, and you'll get a protonated OH2+, and then that will be deprotonated, and you'll end up with your alcohol. So again, this is a review of Chapter 8. Then your next option for adding alcohol across a double bond, or adding alcohol on a double bond, is going to be oxymercuration demercuration. And what I like to say oxymercuration demercuration does is it still follows that Markovnikov rule that we talked about when we were at practice problem 7, where you're going to add your alcohol to the more substituted side, but it doesn't worry about rearrangement. So instead of getting the rearranged product, you're just going to have it add straight across the double bond. So you get your alcohol on the more substituted side, and your proton adds on the other side. And I'm not going to go through the mechanism for that because it's the more complicated one. I'm just trying to work through these practice problems. That is a review of Chapter 8, and I believe the mechanism is shown in your textbook, so you can go back and check that out. And then last but not least, you have hydroboration oxidation. And hydroboration oxidation is the only one that adds anti-Markovnikov. So the alcohol is going to go to the outside instead of to the inside. So this will form, it does like a little box mechanism, and your OH adds on the outside. So those are your 3 options. Now there's only one that looks like our practice problem here, and that is going to be the Markovnikov addition with no rearrangement. So the only option we really have for that is the oxymercuration demercuration. So I want to really encourage you, if you have forgotten some of this, is to go through and say, okay, now how can I add, just draw yourself a little alkene and ask yourself, what happens if I use acid catalyzed addition of an alcohol? What happens if I use oxymercuration demercuration? How will it add? And then finally, what about hydroboration oxidation? and just see if you can come up with the solutions for that as a good review for yourself. Okay, and then we're going to get into practice problem 9. So actually we've already solved practice problem 9 because we worked it out at the beginning. So some students make the error here. We get the rearrangement and you get the carbocation there, and then they just say, now the alcohol is going to add right here. But you have to make sure, like we did on our last practice problem, that you account for rearrangement. So this is not the right answer. This is incorrect. The correct solution, this is about where I realized my phone had gotten cut off, is going to see the rearrangement occur, and you'll end up with your methyl shift happening here, and your carbocation will take its place. And so then your alcohol will add. So your right answer would end up being, let's see, it would do OH2. We already did the mechanism for this in the last one, but just to go over it again. And that would be protonated, and then it would undergo deprotonation. So you'd end up with OH and a methyl group here. So the right answer for this looks like it'd be answer choice C, I believe, that has 1, 2, 3, 1, 2, 3. The alcohol's on a different side, but it's still correct, and then the methyl on the next carbon. So if you're ever not sure, you can count your carbons. We have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. Carbon 2 has a methyl group and an alcohol on it, and carbon 3 has a methyl group. Okay, so that's all review of chapter 8 concepts. The next says the reaction between 1 pentanol and HBr to yield 1 bromopentane is probably. So let's draw that out. Pentane is 5, 1, 2, 3, 1, 2, 3, 4, 5, and it's 1 pentanol, and it's going to yield 1 bromopentane. So the question is, which type of reaction is this? This is really a review of chapters 5 and 6 when you learn about elimination and substitution. So this is not an elimination, because elimination eliminates something, it would leave behind an alkene. So the only option left is a substitution. And you may be thinking, I don't really remember a lot about these types of reactions. I totally understand. These took a long time for me to get. But one thing you can remember is an SN1 type reaction starts much like our acid catalyzed, where it leaves behind a carbocation. And this here is not going to want to form a carbocation on a primary. Those are just very unstable, basically non-existent. So an SN2 would be much more favored. An epoxidation reaction, epoxidation looks like that's an epoxide. We don't have anything close to that, so that's definitely wrong. So even if you're not sure, if you can't remember if it's SN1 or SN2, based on the stuff you do know, you can eliminate it down to 2 answer choices, and then you have a 50-50 shot of getting it right. So that's awesome. Okay, for question 11, which of the following could be used to synthesize 2-bromobutane? So I'm going to draw out these reactions. This looks like bromine, or I'm sorry, 1, 2, 3, 4, butene, not bromine, with Br2, that adds a bromine on both sides, so that's not going to be it. If you do HBr, let's see, what do we have here? So for B, it starts out, I always draw these into bond line because it's way easier for me to see. This looks like CH3, CH2, CH with OH, and a CH3 with HBr. So actually, I would think that this would protonate here, and you'd end up with a good leaving group. So this is going to be basically an SN1 type. The leaving group leaves, and you'll end up with the carbocation, and the bromine will add right here. So that does get us our 2-bromobutane. 1, 2, 3, 4, right here. Okay. I should have probably drawn out bromobutane to begin with, but that's it right there. This is 1,2-dibromobutane. And then here, this alkene, that actually, or alkyne, if this was instead of a triple bond, a double bond, this would work. But because it's a triple bond, I really shouldn't have drawn the bend there. You'd end up with a bromine adding on both sides, or, so the initial addition would look like that, and then it would do another addition of a bromine. So that would not work. If it was an alkene, it would have. And then same thing here with this alkyne, it's going to add 2 bromines on each side. So that's also not going to get us what we want. So the only answer that gets us anywhere close to what we want is answer choice B. Okay, next question is very similar, which could be used to synthesize 1-bromopentane. So 1-bromopentane, I should have drawn this out last time, looks like this. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and a bromo on carbon 1. So this right here is actually pretty promising to me. Let's see. We would first do a protonation. So your alkene would attack, and you'd end up with a carbocation. Then your Br would come add in. Oh, so this is not going to be, I don't think, what we want it to be, because you'd get 2 bromopentane. So that would not work for us. The next option, PBr3, we learned that in this one. This is handy dandy way of converting secondary and primary alcohols into bromine. So literally this would work. And this is one of those mechanisms that you probably just want to memorize, or one of these reactions that you probably just want to memorize. PBr3 and SOCl2 will convert it to a chlorine. That's just something that we went over in this chapter. So that would work. NaBr, I actually think would not work very well. I think you'd add a bromine to both sides because you've got that Na plus there. So I'm not even sure what that would do. Unless maybe the OH would be converted to a better leaving group. I don't even think that that actually would react. And then Br2 with an alcohol, that probably wouldn't react at all. And then here on the bottom, with our alkene, the bromines would add on both sides, which is a reaction we learned in chapter 8. And we saw as well in question 11. So the answer there that's right is answer choice B. Okay, so nice. This is a mesylation. So let's go over the mesylate. So all the mesylates do, or tosylates, is basically convert an alcohol into a good leaving group. So anytime I see that, I cross it out and draw a good leaving group. So our mesylated form is just a good leaving group. And then down here we have an H, and then the CH3 is the same. So that's all that happens. And then the second one, you should recognize this is an SN2 reaction. So this will attack and kick out. It does a backside attack, so there's an inversion of stereochemistry. So this actually becomes, the I will be a dash, and then down here it stays the same, the H and the CH3. So your right answer is going to have your I as a dash and your CH3 as a wedge. So the right answer on that one looks like it's answer choice B to me, because your I is a wedge or a dash, and your CH3 is a wedge. Here they're the same. They're also the same, and you've added an I over here, which that's not going to work at all. And then this is just left on the mesylate form, which this is correct for the mesylate, but it's not the final product. Okay, this next question, actually I'll stop here, upload the video, and then finish off with the last few questions.